Hi, let me just jump right in and say that I've got this theory of gravity, which I've been working on a while now. I'll link in the description. And I found out a few things within it, and I wanted to share it. But first, while I've got your attention, let me reassure you that this is not like a cookie thing from some random guy on YouTube who wants to rant about how he's more intelligent than Einstein and that I figure out everything and something about the luminiferous ether or whatever. This is not what this is about. First, let's talk about the mathematical bar, which is required here for basically to understand, in order to read the paper and understand what is written there, you basically need two mathematical prerequisites. First one, you gotta understand the math of general relativity. And I mean the real actual math. We're talking metric tensors and the Riemann-Christoffel curvature, the Bianchi identities, and so on, the words, basically. And if you happen to find yourself in the situation of already knowing and being fairly familiar with this, then congratulations, you've already done most of the work required to understand it, which I think is a fair proposition because I'm trying to present this thing as a contender, a possible contender to general relativity. And since they can be cast in the same mathematical language, this makes things easier in comparing their performances, so to say. But on top of that, there's the second thing, which would be you gotta understand a little bit of exterior calculus, wedge product, exterior derivatives, and yes, hot star, which is probably the most complicated thing which I've used in this paper. And I'm aware that most physicists, especially experimentalists, are not really familiar with that, but it's not really complicated. I mean, it's basically the modern day version of the vector calculus, which you've probably had to learn before electrodynamics or whatever, something like that. So that's it. This is what you need to This is what we need in order to get the framework, which are this thing called tensor value forms, which I use in order to have a sort of language, a sort of framework with which to cast different theories of gravity plural. Because general relativity is just one example of a theory which you can cast in this framework. But I'm not interested in general relativity. I'm interested in a particular family of theories. Notice I say family and not a single theory, which all share the property which they can, in them, gravity can be thought of as a bona fide force, by which I mean something like the Lorentz force in electrodynamics, or say a leaf as it flows down a river or something like that. What we ordinarily think of as a force, which is not the case with Einstein's ideas. So we gotta clarify a few things because, especially because if you happen to be a physicist, my own experience is that physicists are not very, for whatever reason, they don't seem to be very sophisticated when it comes to philosophy, including, weirdly enough, philosophy of science. So let's try and clarify a few things, right? I'm just gonna throw this out there without proving or anything, but there's this idea very important in the science of falsification, right? Well, falsification does not apply to theories, really. I would say it applies to models. The relation is that theories produce models, which are then tested, and testing the model is what may or may not falsify them. So that's how the dynamic work. Secondly, what do I mean by a theory, which is something which I gave a lot of thought. But long story short, I think in this context, we could just say that the theory is basically a description of the objects which correspond to physical things, to physical objects, to forces and influence and so on, and the mathematical objects which correlate to them. And then you gotta also have some description of typically the differential equations, how these forces evolve over space and time. So, for instance, if you have different Lagrangians, you would have different theories. And in my case, I focus attention in a particular model which is quadratic in the field strength of gravity, because I'm basically copying these ideas from particle physics, right? Where all the forces have the kinetic or free Lagrangian part have a quadratic term in the field strengths. So back to the business of falsification. we gotta have models, right? And a large chunk of this paper is really producing a lot of different models for different systems and purposes. Like there's a little bit of cosmology, there's a little bit of astrophysics, and of course, there's a very important interest case, which is a model for the surrounding field around the sun, which start off as a little point, basically. And we want to know what happened in the vicinity of the sun. So I've worked out a model for that based on the theory. And once I've got the model, I've got a few equations to solve. I could do a little bit of analytical stuff, but then you got to use approximations, and I'm thinking of also later on using numerical methods. But anyway, I figure out a few things here and there.